At the edge of a black hole, reality as we know it unravels. Here, gravity becomes so intense that even light, the fastest thing in the universe, cannot escape its pull. This boundary, known as the event horizon, is not just a cosmic line in the sand. It's a place where the laws of physics, as we understand them, cease to make sense. Picture it as a cosmic point of no return, where space and time twist and stretch beyond recognition. But what truly happens to matter at the edge of a black hole? Where does it go? And what secrets does this mysterious threshold hold about the nature of our universe? In this video, we'll dive into the enigmatic world of black holes, exploring the theories, mysteries, and groundbreaking discoveries that challenge everything we think we know about gravity, space, and time. From the mind-bending concept of spaghettification to the paradoxes that keep scientists up at night, we're about to embark on a journey to decode the edge of a black hole, a place where the universe itself seems to rewrite the rules. The event horizon of a black hole is not just a boundary, it's a cosmic threshold where the known universe begins to unravel. Think of it as the ultimate point of no return, a line drawn by gravity so powerful that nothing, not even light itself, can cross back once it's crossed over. This invisible edge marks the moment when the pull of a black hole becomes inescapable, bending the rules of space and time into something unrecognizable. But how do we even begin to study something so extreme? Enter the Event Horizon Telescope, a global network of observatories that captured the first ever image of a black hole's shadow in 2019. This groundbreaking achievement gave us a glimpse of the event horizon, a place where gravity doesn't just tug, it dominates completely. Stephen Hawking once described the event horizon as a place where the ordinary laws of physics break down, and he wasn't exaggerating. Near this boundary, space-time stretches and twists like taffy pulled to its limit. Imagine standing on the edge of a black hole, watching as time slows to a crawl for someone observing you from afar, while for you, everything rushes forward uncontrollably. It's a paradox that challenges our understanding of reality itself. And yet, this distortion is precisely what makes the event horizon so fascinating. It's a laboratory for testing the limits of Einstein's theory of general relativity. But what would it actually be like to stand at the edge of a black hole? Would you see darkness, or would the warped space-time around you create strange optical illusions? The truth is, no one knows for sure. What we do know is that the event horizon isn't just a scientific curiosity, it's a gateway to the unknown, a place where the universe's deepest secrets might be hiding. So as we peer into this cosmic abyss, one question lingers. If you could stand at the edge of a black hole, what do you think you'd see? The answer might just rewrite everything we think we know. Now let's zoom in on one of the most bizarre and dramatic effects of a black hole's immense gravity, spaghettification. This isn't just a playful name, it's a vivid description of what happens to anything unlucky enough to venture too close. Imagine a piece of taffy being pulled from both ends, stretching thinner and thinner until it's a long, wispy strand. That's essentially what happens to matter near a black hole, but on a cosmic scale. The tidal force's differences in gravitational pull from one side of an object to the other become so extreme that they stretch and compress anything into a thin, elongated shape like cosmic spaghetti. But why does this happen? Picture yourself falling feet first toward a black hole. The gravitational pull on your feet would be much stronger than on your head because they're closer to the black hole's center. This difference in force, known as tidal stretching, would cause your body to elongate dramatically. And it's not just you, planets, stars, or even light itself would undergo this same eerie transformation. It's a process that defies everything we experience in our everyday lives, where gravity feels consistent and predictable. Here, near a black hole, gravity becomes a cosmic sculptor, warping matter in ways that seem almost impossible. Astrophysicists have long been fascinated by spaghettification because it reveals how matter behaves under conditions we can't replicate on Earth. The extreme tidal forces near a black hole aren't just a curiosity, they're a window into the universe's most intense environments. For instance, as an object stretches, it also heats up, emitting radiation that scientists can detect. This phenomenon has allowed researchers to indirectly observe the effects of spaghettification, even from millions of light years away. It's a reminder that black holes aren't just destructive forces, they're also cosmic laboratories, offering clues about the very fabric of reality. What's truly mind-boggling is how spaghettification connects to the broader mysteries of black holes. It's not just about the stretching of matter, it's about how gravity, in its most extreme form, can warp space-time itself. This process hints at the profound interplay between gravity, matter, and energy, challenging our understanding of the universe's fundamental laws. So, the next time you hear about spaghettification, think of it as more than just a cosmic oddity. It's a key piece of the puzzle, helping us unravel the secrets hidden at the edge of a black hole, a place where the universe bends the rules and rewrites the script. For decades, black holes were thought to be the ultimate cosmic vacuums, swallowing everything that crossed their path and allowing nothing, not even light, to escape. But in the 1970s, Stephen Hawking turned this idea on its head with a revolutionary theory. Black holes might not be as impenetrable as we once believed. His groundbreaking concept, now known as Hawking radiation, suggests that black holes can actually emit energy, slowly losing mass over time. This discovery not only challenged our understanding of black holes, but also opened up a new frontier in physics, hinting that even the darkest corners of the universe might hold a glimmer of hope. So, how does this seemingly impossible phenomenon work? To understand Hawking radiation, we need to dive into the bizarre world of quantum mechanics. According to this field of physics, empty space isn't truly empty. Instead, it's a seething sea of virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. Normally, this happens without any noticeable effect, but near the event horizon of a black hole, something extraordinary occurs. If a pair of virtual particles forms right at the edge, one particle might fall into the black hole while the other escapes. The escaping particle becomes real, carrying away a tiny bit of the black hole's energy. Over time, this process causes the black hole to lose mass, slowly evaporating like a cosmic ice cube in the sun. Hawking himself described this phenomenon as a leak in the universe's most secure vault. In his words, black holes aren't as black as they are painted. They are not the eternal prisons they were once thought to be. This radiation is incredibly faint, especially for massive black holes, which can take trillions of years to evaporate completely. But for smaller black holes, the process could happen much faster, releasing bursts of energy that might one day be detectable. It's a humbling reminder that even the most seemingly invincible forces in the universe are subject to change. The implications of Hawking radiation are profound, not just for black holes but for our understanding of the universe itself. If black holes can evaporate, what happens to all the information they've swallowed? According to classical physics, information that falls into a black hole is lost forever. But quantum mechanics suggests that information can't simply disappear, it has to go somewhere. This contradiction, known as the black hole information paradox, remains one of the most hotly debated mysteries in science. It's a puzzle that forces us to rethink the very nature of reality, blending the principles of quantum mechanics and general relativity in ways we're only beginning to grasp. Hawking radiation doesn't just challenge our ideas about black holes, it reshapes how we see the universe. It's a reminder that even in the darkest, most extreme environments, there's always a spark of possibility. So, the next time you think about black holes, remember, they're not just cosmic monsters. They're dynamic, evolving entities revealing secrets about the fabric of space, time, and the very laws that govern our existence. And as we continue to explore their mysteries, one question lingers: what other surprises might these cosmic enigmas hold? The information paradox is one of the most perplexing puzzles in modern physics, a cosmic riddle that strikes at the heart of our understanding of reality. At its core, it asks a simple yet profound question: what happens to the information about matter when it falls into a black hole? According to quantum mechanics, information can never be truly destroyed. It might change form, but it's always preserved. Yet, general relativity tells us that anything crossing a black hole's event horizon is lost forever, crushed into a singularity. These two fundamental theories, each incredibly successful in their own right, seem to clash head-on when it comes to black holes. And that's where the paradox begins. Picture this: you're standing in a library filled with countless books, each one containing unique stories, knowledge, and history. Now imagine that library catches fire, burning every book to ashes. In the real world, the information in those books isn't truly gone. It's still there, just transformed into smoke and ash. But in the case of a black hole, it's as if the library not only burns down, but also the very concept of the books vanishes entirely. The information seems to disappear without a trace, and that's a problem. If information can't be destroyed, as quantum mechanics insists, then where does it go when it's swallowed by a black hole? This paradox has left physicists scratching their heads for decades, but it's also sparked some of the most creative and groundbreaking theories in science. One leading idea is the holographic principle, which suggests that all the information about matter falling into a black hole isn't lost, it's encoded on the event horizon itself, like a cosmic hard drive. Think of it as a two-dimensional hologram containing all the details of a three-dimensional object. In this view, the event horizon becomes a kind of storage device, preserving the information in a way that satisfies quantum mechanics without breaking the rules of general relativity. It's a mind-bending concept, but one that could hold the key to resolving the paradox. Other theories propose that information might escape black holes through Hawking radiation, encoded in subtle ways within the particles emitted. Or perhaps it's stored in the mysterious quantum foam that makes up spacetime at the smallest scales. The truth is, we don't have a definitive answer yet. What we do know is that the information paradox isn't just a theoretical curiosity, it's a clue that could help us bridge the gap between quantum mechanics and general relativity, two pillars of physics that have remained stubbornly separate. Leading physicists like Leonard Susskind and Gerard T. Hooft have spent years wrestling with this paradox, each offering their own insights and interpretations. Susskind, for instance, has championed the idea of black hole complementarity, suggesting that information might exist in two places at once, both inside the black hole and on its surface. Meanwhile, T. Hooft has explored how the holographic principle might apply not just to black holes but to the entire universe, hinting at a deeper, more unified structure to reality. These ideas aren't just academic exercises, they're attempts to solve one of the greatest mysteries of the cosmos. As we grapple with the information paradox, we're not just exploring the fate of matter in black holes, we're probing the very nature of reality itself. How does information survive in the face of such extreme forces? And what does this tell us about the fabric of space, time, and the universe? The answers might lie hidden at the edge of a black hole, where the rules of physics as we know them begin to break down. And as we continue to explore this cosmic conundrum, one thing is clear. The paradox isn't just a problem to solve, it's a doorway to understanding the universe in ways we've only begun to imagine. Deep within the heart of a black hole, beyond the event horizon and the warped space-time that surrounds it, lies the singularity, a point where the known laws of physics collapse into incomprehensibility. Imagine taking all the matter of a star or even an entire galaxy and crushing it into an infinitely small speck. That's the essence of a singularity, a place where density becomes infinite, gravity grows unimaginably strong, and the fabric of space and time itself ceases to function as we understand it. It's like a cosmic crunch where the universe folds in on itself, creating a region where our current scientific tools and theories simply can't reach. The singularity is the ultimate mystery at the core of a black hole, a place where the equations of general relativity, Einstein's masterpiece, break down entirely. According to these equations, as matter falls deeper into the black hole, it's compressed into a single point of infinite density. But infinity isn't just a big number, it's a concept that defies logic and challenges our ability to comprehend. As physicist Kip Thorne once put it, the singularity is where the predictions of general relativity go haywire, where the mathematics fails us, and where we're left staring into the abyss of our own ignorance. What makes the singularity so baffling is that it's not just a physical anomaly, it's a place where time and space lose their meaning. Imagine standing at the singularity if such a thing were possible. Time as you know it would cease to exist. The past, present, and future would all collapse into a single, timeless moment. And space, it would be so distorted that the very idea of here and there would become meaningless. It's a realm where the universe itself seems to reset its rules, leaving us with more questions than answers. Scientists have long struggled to understand what happens at the singularity, not just because it's difficult to study, but because it challenges the very foundations of physics. General relativity, which describes gravity and the large-scale structure of the universe, clashes with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. At the singularity, these two pillars of physics collide in a way that neither can fully explain. As physicist Roger Penrose has noted, the singularity is a place where our current theories hit a wall, and we're left with no choice but to search for new ideas. So, what lies beyond the singularity? Could it be a gateway to another universe, as some theories suggest? Or is it simply the end of the road, a cosmic dead end where matter and energy are erased from existence? These questions push the boundaries of our imagination and force us to rethink what we know about reality. The singularity isn't just a scientific challenge, it's a philosophical one, inviting us to consider the limits of human knowledge and the possibility that some mysteries might remain forever out of reach. As we ponder these questions, one thing becomes clear: the singularity is more than just the heart of a black hole. It's a symbol of the unknown, a reminder that the universe is far stranger and more complex than we can ever fully grasp. And while we may never directly observe or understand what happens at the singularity, the journey to explore it continues to inspire scientists and dreamers alike, pushing us to uncover the secrets of the cosmos one mystery at a time. What if there were shortcuts through the universe, tunnels that could whisk you across unimaginable distances in the blink of an eye? These cosmic passages, known as wormholes, are one of the most tantalizing ideas in theoretical physics. Often depicted in science fiction as gateways to distant galaxies or even alternate realities, wormholes are rooted in real science, specifically in the equations of general relativity. Albert Einstein and physicist Nathan Rosen first proposed the concept in the 1930s, suggesting that these bridges through space-time could exist, connecting two distant points like a fold in a cosmic map. But are wormholes just a fascinating idea, or could they actually be out there waiting to be discovered? To understand how wormholes work, picture the universe as a vast sheet of paper. Normally, traveling from one side to the other would require moving across the entire surface. But what if you could fold the paper, bringing 2 points together and punching a hole through them? That's essentially what a wormhole does. It creates a shortcut through the fabric of space-time, allowing for travel that would otherwise take millions or even billions of years. The idea is both thrilling and daunting, offering the possibility of traversing the cosmos in ways that defy our everyday experience of time and distance. But here's the catch: wormholes, if they exist, are incredibly unstable. According to current theories, they would require exotic matter with negative energy to stay open, something we've never observed in nature. Without this mysterious material, a wormhole would collapse almost instantly, making it useless for travel. This hasn't stopped physicists from exploring the possibilities, though. Renowned scientists like Kip Thorne have studied the mathematics of wormholes, suggesting that they might be more than just theoretical curiosities. Thorne even consulted on the movie Interstellar, helping to create a scientifically plausible depiction of a wormhole. While the film took some creative liberties, it sparked widespread interest in the idea that wormholes could one day become a reality. The connection between wormholes and black holes adds another layer of intrigue. Some theories suggest that the intense gravitational forces near a black hole's event horizon could potentially create the conditions needed for a wormhole to form. Imagine a black hole acting as one end of the tunnel, with the other end opening up somewhere else in the universe, or even in another universe entirely. It's a mind-bending concept that bridges the gap between science and imagination, offering a glimpse of how the universe might hide secrets we've only begun to uncover. Despite their theoretical appeal, wormholes remain shrouded in mystery. Could they ever be stable enough for humans to traverse? Would they lead to distant galaxies or to places beyond our current understanding of reality? These questions push the boundaries of physics and inspire us to dream of a future where the stars are within reach. And as we continue to explore the mysteries of black holes, wormholes remind us that the universe is full of possibilities, waiting for us to find the keys to unlock them. So, the next time you look up at the night sky, remember, the cosmos might be far more connected than we ever imagined. Now, let's step into one of the most mind-bending effects of a black hole's immense gravity: time dilation. Imagine you're holding a clock as you approach the edge of a black hole. To someone watching from a safe distance, your clock would appear to tick slower and slower, as if time itself were stretching out like taffy. This isn't just science fiction, it's a real phenomenon predicted by Einstein's theory of general relativity. Near a black hole where gravity is at its most extreme, time doesn't flow at the same steady pace we're used to. Instead, it warps, slowing down dramatically the closer you get to the event horizon. It's as if the universe itself has hit the brakes, creating a cosmic time warp that challenges everything we think we know about the passage of time. To put it in simpler terms, think of time as a river. On Earth, it flows smoothly and predictably, carrying us along at a constant rate. But near a black hole, the river slows to a crawl, and in some places it might even seem to stop altogether. This effect, known as gravitational time dilation, means that time passes differently depending on where you are in relation to the black hole. For someone falling toward the event horizon, time might feel normal, but for an observer far away, it would appear as though the traveler's movements have slowed to a glacial pace. It's a strange and counterintuitive idea, but one that's been confirmed by experiments here on Earth, like the precise atomic clocks on GPS satellites, which tick slightly faster in orbit where gravity is weaker. The implications of time dilation are profound, not just for black holes but for our understanding of the universe itself. If you could somehow survive a trip near a black hole, you might return to find that centuries or even millennia have passed on Earth, while for you, only a short time has elapsed. This raises intriguing questions about the nature of time. Is it truly universal, or is it more fluid, shaped by the forces around us? Physicists like Kip Thorne have explored these questions, suggesting that time dilation could one day play a role in space travel, allowing us to traverse vast distances without aging as much as those left behind. But time dilation isn't just a theoretical curiosity, it's a reminder of how gravity shapes the fabric of reality. Near a black hole where gravity is strongest, time bends and twists in ways that seem almost magical. And yet, it's all governed by the same laws that keep planets in orbit and stars burning brightly. This strange interplay between gravity and time challenges us to rethink what we know about the universe, pushing the boundaries of both science and imagination. So, if you could stand at the edge of a black hole, watching time slow to a crawl, what would it feel like? Would it be exhilarating, terrifying, or something entirely beyond words? And how would it change your perspective on the passage of time? These questions don't just belong to physicists, they are for all of us to ponder as we explore the mysteries of a universe that's far stranger and more wonderful than we ever imagined. At the centers of some galaxies, black holes unleash one of the most awe-inspiring phenomena in the universe: jets of particles that streak across space at nearly the speed of light. These jets, often stretching for thousands of light years, are like cosmic fire hoses, spraying energy and matter into the void with unimaginable force. But how do these jets form, and what can they tell us about the hidden mechanics of black holes? The answer lies in the chaotic environment surrounding these cosmic giants, where gravity, magnetic fields, and swirling matter combine to create something truly extraordinary. Picture a black hole as a cosmic engine, spinning at incredible speeds and devouring everything in its path. As matter spirals inward, forming a glowing disk of superheated gas called an accretion disk, not all of it gets swallowed. Some of it gets caught in the black hole's intense magnetic fields and flung outward along its poles. This process, powered by the black hole's rotation and magnetic forces, launches streams of particles into space at velocities so high they defy comprehension. It's as if the black hole is squeezing a cosmic tube of toothpaste, but instead of minty freshness, it's spraying high-energy particles across the universe. These jets aren't just spectacular to look at, they play a crucial role in shaping the cosmos. As they blast through space, they carry energy and matter far beyond their host galaxies, influencing the formation of stars and even entire galaxy clusters. Think of them as cosmic sculptors, carving out vast regions of space and seeding the universe with the raw materials for new structures. Astrophysicists have observed that the energy released by these jets can heat surrounding gas, preventing it from collapsing into stars and effectively putting the brakes on galaxy growth. In this way, black hole jets are more than just cosmic fireworks, they're key players in the evolution of the universe. But what powers these jets to such incredible speeds? The answer lies in the interplay between the black hole's spin and its magnetic fields. As the black hole rotates, it drags space-time around with it, twisting magnetic fields into tightly wound spirals. These fields act like cosmic slingshots, accelerating particles to nearly the speed of light. Renowned astrophysicist Roger Blandford once described this process as a natural particle accelerator, comparing it to the most powerful machines humans have ever built, but on a scale that dwarfs anything we could imagine. The energy released in these jets can outshine entire galaxies, making them some of the brightest objects in the universe. The study of black hole jets has opened up new frontiers in astrophysics, revealing how these cosmic engines influence their surroundings on enormous scales. For instance, observations from telescopes like the Chandra X-ray Observatory have shown that jets can create shock waves in intergalactic gas, sparking regions of intense heat and turbulence. These findings have led scientists to rethink how black holes interact with their environments, showing that they're not just passive consumers of matter but active shapers of the cosmos. So, what do these jets tell us about the broader mysteries of the universe? They're a reminder that black holes are more than just destructive forces. They're dynamic, energetic phenomena that drive the evolution of galaxies and the large-scale structure of the cosmos. And as we continue to study these cosmic particle accelerators, we're uncovering clues about the fundamental forces that govern the universe. From the magnetic fields that power them to the incredible speeds they reach, black hole jets are a testament to the universe's ability to surprise and inspire. And as we peer deeper into the cosmos, one question remains: what other secrets might these jets hold, waiting to be discovered? At the heart of nearly every galaxy, including our own Milky Way, lies a cosmic giant so massive it defies comprehension. These are supermassive black holes, behemoths that can weigh billions of times more than our Sun. Unlike their smaller stellar counterparts, which form from collapsing stars, supermassive black holes are the anchors of their galaxies, holding entire star systems in their gravitational grip. Imagine a colossal anchor dropped into the cosmic ocean, its immense weight shaping the currents and tides around it. That's the role supermassive black holes play in the universe, central, gravitational powerhouses that influence everything around them. But how do these giants form? The origins of supermassive black holes remain one of the most intriguing mysteries in astrophysics. Some theories suggest they could have started as smaller black holes, merging and growing over billions of years by devouring stars, gas, and even other black holes. Others propose they might have formed directly from the collapse of massive clouds of gas in the early universe, bypassing the star stage entirely. What we do know is that their growth is fueled by the chaotic environment at the centers of galaxies, where swirling disks of gas and dust feed their insatiable appetites. Over time, they grow to staggering sizes, becoming the dominant forces in their galactic homes. Their immense size isn't just for show. Supermassive black holes play a crucial role in shaping the galaxies they inhabit. For instance, their gravitational pull can trigger the formation of new stars by compressing gas clouds, while their powerful jets and radiation can also prevent star formation by heating up surrounding material. It's a delicate balance, one that determines whether a galaxy becomes a bustling stellar nursery or a quiet, aging expanse. Astronomers have observed that galaxies with active supermassive black holes often have fewer stars forming, suggesting these giants are more than just passive observers. They're active participants in galactic evolution. The discovery of supermassive black holes has revolutionized our understanding of the cosmos. In the 1960s, astronomers like Martin Schmidt identified quasars, extremely bright objects powered by supermassive black holes billions of light years away. These discoveries revealed that supermassive black holes were not only real but also common, lurking at the centers of galaxies across the universe. Today, thanks to instruments like the Hubble Space Telescope and the Event Horizon Telescope, we've been able to peer closer than ever before, capturing images of the supermassive black hole at the center of the Milky Way, known as Sagittarius A. Each observation brings us closer to understanding these cosmic giants and their role in the universe. But what secrets do supermassive black holes hold about the universe's origins? Could they offer clues about how galaxies formed and evolved over billions of years? Some scientists believe that studying these giants might even shed light on the early universe, revealing how the first structures emerged from the chaos of the Big Bang. The answers to these questions are still hidden, waiting to be uncovered in the depths of space. As we continue to explore these cosmic anchors, we're not just learning about black holes, we're piecing together the story of the universe itself. And with every discovery, we're reminded that the cosmos is far more interconnected and dynamic than we ever imagined. While most black holes we know of are either born from collapsing stars or lurk as supermassive giants at the center of galaxies, there's another type that might have existed since the dawn of the universe itself. These are primordial black holes, tiny, ancient relics thought to have formed in the chaos of the Big Bang. Unlike their stellar or supermassive cousins, primordial black holes didn't come from dying stars or galactic mergers. Instead, they're believed to have emerged from the intense density fluctuations in the early universe, like cosmic seeds planted in the first moments of creation. But what makes these mysterious objects so intriguing, and could they still be out there, hidden in the fabric of space and time? Imagine the universe in its infancy, a hot, dense soup of energy and matter. In this primordial chaos, tiny pockets of material could have collapsed under their own gravity, forming black holes no larger than an atom or as massive as a mountain. These primordial black holes would have been scattered throughout the cosmos, silently drifting through space for billions of years. Unlike stellar black holes, which form from the collapse of massive stars, or supermassive black holes, which grow over eons, primordial black holes are like cosmic time capsules, tiny windows into the universe's earliest moments. One of the most fascinating ideas about primordial black holes is their potential connection to dark matter, the invisible substance that makes up most of the universe's mass. While dark matter has never been directly detected, some scientists believe primordial black holes could be a key piece of the puzzle. If these ancient objects exist in large numbers, they might account for some or even all of the dark matter we observe. It's a tantalizing possibility, suggesting that the universe's greatest mystery might be tied to its oldest structures. As cosmologist Bernard Carr has noted, primordial black holes could be the missing link between the Big Bang and the dark matter we see today. The search for these elusive objects is no easy task because they're so small and dark. Primordial black holes are incredibly difficult to detect, but scientists have come up with creative ways to look for them. One method involves observing gravitational microlensing, where a passing black hole bends the light from a background star, causing it to briefly brighten. Another approach relies on looking for the telltale bursts of radiation that might occur if a primordial black hole evaporated completely through Hawking radiation. While no definitive evidence has been found yet, the hunt is far from over, and each new observation brings us closer to answering this cosmic question. What's truly exciting is the potential for primordial black holes to reshape our understanding of the universe. If they exist, they could provide clues about the conditions of the early universe, helping us piece together the story of how everything began. They might also offer insights into the nature of dark matter, shedding light on one of the greatest mysteries in physics. And who knows, they could even hold secrets about the fundamental laws of the cosmos waiting to be uncovered. So, as we peer into the depths of space, searching for these ancient relics, one thing is clear: primordial black holes are more than just a scientific curiosity. They're a reminder that the universe is full of surprises, and that even the smallest objects can hold the keys to the biggest questions. Could these cosmic seeds be the missing piece of the puzzle, hidden in plain sight all along? The answer might just change everything we think we know about the cosmos. When two black holes collide, the universe doesn't just witness a cosmic crash, it experiences a symphony of ripples that echo across spacetime itself. These ripples, known as gravitational waves, are the result of one of the most violent and energetic events in the cosmos. Picture two massive dancers spinning closer and closer in a deadly embrace, their gravity warping the fabric of the universe as they spiral inward. When they finally merge, the impact sends shockwaves through spacetime like a stone dropped into a still pond. These waves travel across the cosmos, carrying with them a story of colossal forces and hidden truths about the nature of gravity. The first direct detection of gravitational waves in 2015 by the LIGO Observatory was a groundbreaking moment in science. It confirmed a prediction made by Albert Einstein a century earlier and opened a new window into the universe. Unlike light, which can be blocked or distorted, gravitational waves pass through everything, allowing us to listen to the universe in a way we never could before. Each wave carries a unique signature, revealing details about the black holes that created it, their masses, spins, and even the direction of their orbits. It's as if the universe is whispering its secrets to us, one ripple at a time. But what exactly happens during a black hole collision? As two black holes orbit each other, they lose energy in the form of gravitational waves, drawing closer together in a spiral that can last millions of years. In the final moments, they merge into a single, more massive black hole, releasing a burst of energy so powerful that it can briefly outshine all the stars in the observable universe combined. The newly formed black hole then rings down, settling into its final state and sending out a final set of waves that fade into the cosmic background. It's a process that's both violent and elegant, a testament to the incredible forces at play in the universe. The discovery of gravitational waves has revolutionized our understanding of black holes. Before LIGO, most of what we knew about black holes came from observing their effects on surrounding matter, light bending around them, jets shooting from their poles, or stars orbiting their invisible centers. But gravitational waves allow us to study black holes directly, even when they're isolated in the void of space. This has led to some surprising findings. For instance, LIGO has detected black hole mergers involving objects much larger than expected, challenging our theories about how black holes form and grow. Physicists like Kip Thorne and Rainer Weiss, who are instrumental in the development of LIGO, have described these discoveries as a new era in astronomy. It's like we've been watching a silent movie all our lives, and suddenly the sound has been turned on. Thorne once remarked, "These waves don't just tell us about black holes, they reveal the dynamic, ever-changing nature of the universe itself." From the birth of black holes to the mergers that shape their evolution, gravitational waves offer a front-row seat to the cosmic drama. So, what can these collisions teach us about the nature of gravity? Each merger is a laboratory for testing Einstein's theory of general relativity, pushing it to its limits in ways that were once thought impossible. By studying the ripples from these events, scientists can explore how gravity behaves in the most extreme conditions, probing the boundaries of our understanding. And as we continue to detect more mergers, we're uncovering clues about the universe's history, from the formation of the first black holes to the large-scale structure of the cosmos. Black hole collisions are more than just cosmic spectacles, they're windows into the heart of gravity itself. They remind us that the universe is alive with motion and energy, constantly reshaping itself in ways we're only beginning to understand. And as we listen to the echoes of these distant mergers, one question lingers: what other secrets might the universe be hiding, waiting for us to uncover? Black holes, for all their mystery and complexity, might be hiding a surprisingly simple secret. Imagine trying to describe a star or a planet. You'd need to account for its composition, temperature, magnetic fields, and countless other details. But when it comes to black holes, the rules are different. According to the No-Hair Theorem, a black hole can be fully described by just three properties: its mass, its electric charge, and its spin. That's it. No matter how complex the object that formed the black hole, whether it was a massive star, a swirling cloud of gas, or even an entire galaxy once it crosses the event horizon, all that complexity is stripped away, leaving behind a cosmic fingerprint defined by just these three numbers. This idea, first proposed by physicist John Archibald Wheeler in the 1960s, suggests that black holes are remarkably simple compared to other cosmic objects. Think of it like this: if a star is a sprawling novel with countless characters and plot twists, a black hole is a haiku, elegant, minimal, and distilled to its essence. The No-Hair Theorem gets its name from the idea that black holes have no hair, or no extra details beyond these three fundamental properties. It's as if the universe itself has a way of simplifying the most extreme objects it creates. But why is this simplicity so fascinating? For one, it challenges our expectations. Black holes are often thought of as chaotic, destructive forces, yet the No-Hair Theorem suggests an underlying order. It tells us that no matter how a black hole forms, its final state is determined purely by these three parameters. This has profound implications for our understanding of black holes, hinting that they might be the ultimate cosmic equalizers, erasing all traces of their origins and leaving behind a clean, universal signature. Of course, like any good theory, the No-Hair Theorem has its limitations. Some physicists argue that it might not hold true in all cases, especially when quantum mechanics comes into play. For instance, quantum effects could potentially allow black holes to retain some hair or additional information, challenging the theorem's simplicity. Others have explored how exotic objects like wormholes or black holes in higher dimensions might break the rules, adding layers of complexity to what we thought was a straightforward idea. Renowned physicist Stephen Hawking once quipped, "Black holes ain't as bald as they're painted," suggesting that there's still more to uncover. Yet, despite these exceptions, the No-Hair Theorem remains a cornerstone of black hole physics. It's a reminder that even in the most extreme environments, the universe operates by elegant, often surprising rules. And as we continue to explore the mysteries of black holes, this theorem raises an even bigger question. If black holes are so simple on the outside, what secrets are they hiding on the inside? What lies beyond the event horizon where the laws of physics as we know them begin to break down? The answers might just rewrite everything we think we know about the cosmos. At first glance, the idea of heat in the frigid depths of a black hole seems like a contradiction. After all, black holes are notorious for their intense gravitational pull and their ability to swallow light and matter, leaving behind a cold, dark void. Yet, beneath this seemingly lifeless exterior lies a surprising connection to one of the most fundamental branches of science, thermodynamics. This field, which deals with heat, energy, and the behavior of systems, has revealed that black holes are not just cosmic vacuum cleaners, they're intricate engines humming with hidden activity. To understand this, let's start with a simple question. How can something so cold have heat? The answer lies in the groundbreaking work of physicist Jacob Bekenstein, who proposed that black holes possess a property called entropy. Entropy is a measure of disorder or randomness in a system, and it's a cornerstone of thermodynamics. Bekenstein argued that black holes must have entropy because they absorb matter and energy, effectively increasing the disorder of the universe. It's like adding more pieces to a jigsaw puzzle without knowing where they fit. The complexity grows, even if we can't see it directly. Stephen Hawking took this idea even further, revealing that black holes aren't just passive collectors of entropy, they also emit radiation. This radiation, now known as Hawking radiation, is the result of quantum effects near the event horizon, where pairs of particles and antiparticles pop into existence. Occasionally, one particle falls into the black hole while the other escapes, carrying away a tiny bit of energy. Over time, this process causes the black hole to lose mass and, in a sense, evaporate. It's as if the black hole is a cosmic engine, slowly releasing heat into the cold void of space. But what does this mean for our understanding of black holes? For one, it suggests that they're far more dynamic than we once thought. Like a steam engine converting heat into motion, a black hole converts matter and energy into entropy and radiation. This connection between gravity and thermodynamics has profound implications for physics, hinting at a deeper unity between the laws that govern the very large and the very small. It's a bridge between general relativity and quantum mechanics, two theories that have long resisted unification. the implications of black hole thermodynamics stretch even further. If black holes have entropy, they must also have temperature, a concept that seems almost paradoxical given their icy reputation. Yet, this temperature is incredibly low, often just fractions of a degree above absolute zero. The larger the black hole, the colder it is, making it a cosmic paradox, a massive, dark object that emits faint heat. This revelation has forced scientists to rethink the nature of black holes, transforming them from simple gravitational wells into complex thermodynamic systems. Perhaps the most profound insight from this connection is the idea that black holes might hold clues about the fundamental nature of reality. As physicist Leonard Susskind once put it, black holes are the Rosetta Stones of physics. They encode information about the universe in ways we're only beginning to decipher, offering tantalizing hints about how gravity, quantum mechanics, and thermodynamics might fit together. This interplay between heat, entropy, and black holes isn't just a scientific curiosity, it's a key to unlocking some of the universe's deepest mysteries. So, how can something so cold have heat? The answer lies in the strange, counterintuitive world of black holes, where the rules of thermodynamics meet the extremes of gravity and quantum mechanics. As we explore this cosmic engine, we're reminded that even the darkest corners of the universe are alive with activity, humming with energy and hidden order. And as we continue to unravel these mysteries, one thing is certain: black holes are far more than just voids, they're windows into the very fabric of reality itself. What if the edge of a black hole isn't just a quiet, invisible boundary, but a raging inferno? This is the startling idea behind the Firewall Paradox, a theory that suggests a blazing wall of energy might exist at the event horizon. Imagine approaching the edge of a black hole, expecting to cross into the unknown, only to be met with a cosmic barrier so intense it could incinerate anything that comes near. This fiery wall isn't just a dramatic twist in the story of black holes, it's a puzzle that challenges everything we think we know about gravity, quantum mechanics, and the very nature of reality. The Firewall Paradox emerged from a clash between two of physics' most successful theories, general relativity and quantum mechanics. General relativity tells us that an object falling into a black hole would cross the event horizon smoothly, feeling no dramatic effects, a concept known as the no-drama principle. But quantum mechanics paints a different picture. According to this theory, the intense gravitational forces near the event horizon should create a chaotic, high-energy environment, potentially resulting in a wall of fire that destroys anything entering the black hole. It's like expecting to step through a doorway only to find it's a wall of flames. So, which one is it, fire or no fire? The answer depends on who you ask. The debate over firewalls has divided physicists for years, with some arguing that they're a necessary consequence of quantum mechanics, while others see them as a sign that our understanding of physics is incomplete. Leading researchers like Leonard Susskind have described the paradox as a crisis in physics, forcing us to question whether our theories can truly coexist. Susskind, along with physicist Joseph Polchinski, has explored how firewalls might resolve the black hole information paradox, suggesting that the destruction of information at the event horizon could be a way to preserve the laws of quantum mechanics. But not everyone agrees. Some physicists argue that firewalls violate the principles of general relativity, which predict a smooth transition across the event horizon. It's a cosmic tug-of-war, with each side presenting compelling arguments but no clear winner in sight. To grasp why this paradox is so important, think of it as a cosmic litmus test for our understanding of the universe. If firewalls exist, they could fundamentally change how we view black holes, turning them from mysterious voids into fiery gates that guard the secrets of the cosmos. On the other hand, if firewalls don't exist, we might need to rethink our understanding of quantum mechanics or find a new way to reconcile it with general relativity. Either way, the paradox pushes us to rethink what we know and explore new possibilities. So, what could the existence or absence of firewalls tell us about the universe? For one, it might hold the key to understanding how information is preserved in black holes, a question that has puzzled physicists for decades. It could also shed light on the nature of spacetime itself, revealing whether it's smooth and continuous or riddled with quantum fluctuations. And as we continue to explore this paradox, we're reminded that the universe is full of surprises, always ready to challenge our assumptions and push the boundaries of our knowledge. The firewall paradox isn't just a scientific debate, it's a window into the heart of one of the greatest mysteries in physics. It forces us to confront the limits of our understanding and inspires us to ask deeper questions about the nature of reality. And as we peer into the flames of this cosmic puzzle, one thing is certain: the answers we find might just rewrite the rules of the universe as we know them. In 2019, humanity achieved something once thought impossible. We captured an image of a black hole. Not just any image, but a glimpse of the shadow cast by a supermassive black hole at the center of the galaxy M87, 55 million light-years away. This cosmic silhouette, captured by the Event Horizon Telescope, isn't a photograph in the traditional sense. Instead, it's a composite of data collected by a global network of radio telescopes working together like pieces of a gigantic cosmic puzzle. The result, a fiery ring of light surrounding a dark, circular void, a shadow that marks the event horizon, the point where light itself is swallowed by the black hole's immense gravity. To understand how this image was created, think of the Event Horizon Telescope as a virtual telescope the size of Earth itself. By synchronizing observations from observatories across the globe, scientists were able to achieve the resolution needed to peer into the heart of a black hole. The process involved collecting petabytes of data, which was then painstakingly analyzed and reconstructed into the now iconic image. It's like trying to piece together a jigsaw puzzle where the pieces are scattered across the planet, and the picture is something no one has ever seen before. The result was a groundbreaking moment, not just for astrophysics, but for our understanding of the universe itself. But what does this shadow actually tell us? The dark center of the image isn't the black hole itself, it's the absence of light. A region where gravity is so strong that nothing, not even light, can escape. Surrounding it is a glowing ring of superheated gas spiraling inward, bending around the black hole like a cosmic halo. This ring of light is distorted by the black hole's intense gravitational field, creating a visual fingerprint that confirms predictions made by Einstein's theory of general relativity over a century ago. As astrophysicist Shepard Doleman, who led the project, put it, "We've seen what we thought was unseeable." The significance of this achievement can't be overstated. For the first time, we have direct visual evidence of a black hole, an object that was once purely theoretical. This image doesn't just confirm the existence of black holes, it offers a new way to study their properties, from their size and shape to the behavior of matter and energy in their vicinity. It's like having a new tool in our cosmic toolkit, one that allows us to explore the universe's most extreme environments in unprecedented detail. And for scientists, it's a reminder that even the most abstract ideas can eventually be tested and proven. What's truly remarkable is how this image challenges our perceptions. Black holes are often thought of as invisible, but their shadows reveal a hidden dimension of their existence. It's a bit like seeing the outline of a figure in a dimly lit room. You can't see the details, but you know something monumental is there. This cosmic silhouette has opened up new avenues for research, from studying the dynamics of accretion disks to testing the limits of general relativity in the most extreme conditions. And as we continue to refine our techniques, future images could reveal even more about these enigmatic objects. So, what can we learn from the shadows of black holes? For one, they're a reminder that even in the darkest corners of the universe, there are clues waiting to be uncovered. They challenge us to push the boundaries of our technology and imagination, to see the unseen and explore the unknown. And as we peer into these cosmic shadows, we're not just observing black holes, we're uncovering the secrets of the universe itself, one shadow at a time. At the heart of nearly every galaxy lies a cosmic architect, shaping the vast structures that define the universe. These architects are supermassive black holes, titans of gravity that don't just inhabit galaxies, they build them. Imagine a sculptor working on a masterpiece, carving out shapes and guiding the flow of material. That's the role black holes play in the cosmos, but instead of chisels and clay, they use gravity, radiation, and jets of high-energy particles to mold their surroundings. Their influence stretches far beyond their event horizons, shaping the birth of stars, the growth of galaxies, and even the fate of entire galaxy clusters. One of the most fascinating ways black holes shape galaxies is through a process called feedback. Think of it as a cosmic thermostat, regulating the temperature and density of gas in a galaxy. When a black hole feeds on surrounding matter, it doesn't just consume quietly, it releases tremendous amounts of energy in the form of radiation and jets. These outbursts can heat up nearby gas, preventing it from cooling and collapsing into stars. It's like a gust of wind blowing away the clouds before they can rain, effectively putting the brakes on star formation. This feedback mechanism ensures that galaxies don't grow too quickly or burn through their fuel too soon, maintaining a delicate balance between creation and destruction. But black holes don't just stifle star formation, they can also ignite it. In some cases, the shock waves from their jets compress gas clouds, triggering the birth of new stars. It's a bit like lighting a match in a field of dry grass, creating pockets of fire where none existed before. Astronomers have observed this phenomenon in galaxies like Centaurus A, where jets from the central black hole spark star formation along their path. This dual role, suppressing and stimulating star birth, makes black holes pivotal players in the life cycle of galaxies, acting as both destroyers and creators in the cosmic dance. The connection between black holes and galaxies runs even deeper. Studies have shown that the mass of a galaxy's central black hole is closely linked to the size and structure of its host galaxy. Larger galaxies tend to have more massive black holes, suggesting a symbiotic relationship that has evolved over billions of years. Astrophysicists like Andrea Ghez, who shared the Nobel Prize for her work on black holes, have described this relationship as a cosmic handshake, where black holes and galaxies grow together, each influencing the other in profound ways. This interplay isn't just a coincidence, it's a fundamental part of how the universe organizes itself. What's truly remarkable is how black holes shape galaxies on the largest scales. Their jets and radiation can extend far beyond their host galaxies, influencing the formation of galaxy clusters and the distribution of matter in the universe. It's as if black holes are the unseen threads weaving the cosmic tapestry, connecting galaxies across vast distances and shaping the large-scale structure of the cosmos. Without their influence, the universe might look very different, less organized, less dynamic, and far less rich in structure. So, as we marvel at the beauty of galaxies, from the spiraling arms of the Milky Way to the glowing cores of distant quasars, let's not forget the architects behind the scenes. Black holes are more than just cosmic curiosities, they're the master builders of the universe, shaping the galaxies we see today and influencing the future of the cosmos. And as we continue to explore their mysteries, we uncover not just the secrets of black holes, but the story of how the universe itself came to be. What other cosmic blueprints might these giants hold, waiting to be discovered? The answer lies in the stars and the black holes that shape them. In the vast expanse of the universe, there's a mystery that has puzzled scientists for decades: dark matter. This invisible substance makes up about 85% of the universe's mass, yet it doesn't emit, absorb, or reflect light. It's like a cosmic ghost, silently influencing the motion of galaxies and the structure of the cosmos without ever revealing itself. But what if this elusive dark matter is connected to one of the universe's most enigmatic objects, black holes? Could these cosmic giants, born from the collapse of stars or the chaos of the early universe, hold the key to unraveling one of science's greatest mysteries? One intriguing possibility is that some dark matter could be made up of primordial black holes, ancient relics thought to have formed in the first moments after the Big Bang. Unlike the black holes we're familiar with, which form from collapsing stars, primordial black holes are much smaller, ranging from the size of an atom to the mass of a mountain. These tiny, ancient objects could have been scattered throughout the universe like cosmic seeds, silently drifting through space for billions of years. If they exist, they might account for at least some of the dark matter we observe, acting as invisible anchors that shape the cosmos without ever being seen. Detecting these primordial black holes, however, is no easy task because they're so small and dark. They don't emit light or radiation in the way larger black holes do. But scientists have come up with creative ways to search for them. One method involves looking for gravitational microlensing events, where a passing black hole bends the light from a distant star, causing it to briefly brighten. Another approach focuses on the faint bursts of radiation that might occur if these black holes evaporate completely through Hawking radiation. While no definitive evidence has been found yet, the search continues, driven by the tantalizing possibility that these ancient objects could solve the dark matter puzzle. Cosmologists like Bernard Carr have long speculated about the role primordial black holes might play in the universe. If they exist, Carr has said, they could be the missing link between the Big Bang and the dark matter we see today. This idea challenges us to rethink not just the nature of dark matter, but also the origins of black holes themselves. It's a reminder that the universe often hides its secrets in plain sight, waiting for us to uncover them. But the connection between black holes and dark matter goes even deeper. Some theories suggest that dark matter particles could accumulate around black holes, creating dense halos that influence their growth and behavior. Others propose that black holes might act as cosmic traps, capturing dark matter and revealing its presence through subtle gravitational effects. These ideas open up new avenues for research, offering fresh ways to explore the hidden corners of the universe. So, could black holes hold the key to understanding dark matter? The answer might lie in the interplay between these two cosmic mysteries, each shedding light on the other in ways we're only beginning to understand. As we continue to probe the depths of space, searching for clues to these invisible forces, one thing is certain: the universe is full of surprises, and the answers we seek might be closer than we think. What other secrets might these cosmic ghosts reveal as we unravel the story of the universe? The journey to find out is just beginning. What if black holes aren't just cosmic vacuum cleaners, but gateways to entirely new universes? This mind-bending idea suggests that these enigmatic objects could be portals to other dimensions, part of a vast multiverse where countless realities exist alongside our own. It's a concept that sounds like science fiction, but it's rooted in some of the most cutting-edge theories in physics. Imagine a black hole not as a dead end, but as a cosmic doorway, a place where the fabric of space-time bends so dramatically that it could connect our universe to another. This is the speculative yet tantalizing idea that black holes might be the keys to unlocking the mysteries of the multiverse. To understand how this could work, let's revisit the concept of wormholes, those hypothetical tunnels through space-time that could link distant points in the universe, or even different universes entirely. Wormholes are predicted by the equations of general relativity, but they've never been observed. Some scientists speculate that black holes could be the entrance points to these cosmic shortcuts. Picture a black hole as one end of a wormhole, with the other end opening into another universe or a distant part of our own. It's like finding a hidden passage in a vast cosmic mansion, one that could take you to places you never imagined existed. This idea ties into quantum mechanics, which suggests that particles can exist in multiple states at once, and that the universe itself might be just one of many in an infinite multiverse. Physicists like Leonard Susskind have explored how black holes might connect to this multiverse, proposing that the information swallowed by a black hole isn't lost but encoded on its surface, potentially linking it to another reality. It's a bit like a cosmic puzzle where each piece fits into a larger, more complex picture that we're only beginning to see. But what would it mean if black holes are truly portals to other universes? For one, it could reshape our understanding of reality itself. Instead of seeing the universe as a singular, isolated entity, we might come to view it as part of a vast network of interconnected realities, each with its own laws of physics and possibilities. This idea has profound implications for everything from cosmology to philosophy, challenging us to rethink what we know about existence and our place in the cosmos. Of course, this theory isn't without its challenges. The multiverse remains a speculative concept, and the idea of black holes as gateways is still far from proven. Physicists like Stephen Hawking and Kip Thorne have cautioned that while the math might allow for such possibilities, the practical realities like the immense gravitational forces and the instability of wormholes make it unlikely we'll ever travel through one. Yet, even if black holes aren't literal portals, the idea pushes us to explore the boundaries of science and imagination, inspiring new questions about the nature of the universe. So, what might lie on the other side of a black hole? Another universe, a parallel reality, or something entirely beyond our comprehension? The answer, if there is one, remains hidden in the shadows of these cosmic enigmas. But as we continue to probe the mysteries of black holes, we're reminded that the universe is far stranger and more interconnected than we ever imagined. And who knows, the next great discovery might just reveal that black holes are more than just cosmic curiosities. They're the keys to unlocking the secrets of the multiverse itself. As we push the boundaries of our understanding of black holes, we're faced with a question that goes beyond science. What are the ethical implications of probing the universe's most extreme phenomena? Imagine a cosmic experiment where humanity tinkers with forces so powerful they could reshape the fabric of reality itself. This isn't science fiction. It's a very real consideration as we explore the mysteries of black holes, especially when it comes to experiments that might recreate these cosmic giants in miniature form. Could our quest for knowledge inadvertently unleash something we can't control? It's a question that ethicists and scientists alike have grappled with as the line between discovery and danger becomes increasingly blurred. One of the most debated scenarios involves particle accelerators like the Large Hadron Collider. These massive machines, designed to smash particles together at nearly the speed of light, have raised concerns about the possibility of creating microscopic black holes. While the idea sounds like something out of a disaster movie, the scientific community has thoroughly assessed the risks. According to physicists like Stephen Hawking and others, any black holes created in such experiments would be so tiny and unstable that they'd evaporate almost instantly through Hawking radiation. Still, the ethical question remains, should we even take that chance? It's a delicate balance between the pursuit of knowledge and the responsibility to safeguard our planet. Ethicists have weighed in on this debate, emphasizing the importance of precautionary principles. Just as a scientist wouldn't conduct an experiment without safety protocols, humanity must approach black hole research with a similar mindset. Safeguards are in place to ensure that experiments are conducted responsibly, with rigorous oversight and risk assessment. But the deeper question is one of intent. How far should we go in our quest to understand the cosmos? Are we willing to risk the unknown for the sake of discovery, or should we proceed with caution, prioritizing safety over curiosity? This tension lies at the heart of scientific progress, reminding us that every step forward comes with its own set of challenges. The metaphor of a cosmic experiment isn't just about the risks, it's also about the rewards. By studying black holes, we're not just exploring the universe, we're testing the limits of human ingenuity and resilience. These experiments push the boundaries of what we know, challenging us to think creatively and solve problems we've never faced before. But they also force us to confront our own limitations, asking us to consider the consequences of our actions on a cosmic scale. It's a humbling reminder that the universe is far more complex than we can imagine, and that our understanding of it is still in its infancy. So, how far should we go in our quest to understand black holes? The answer isn't simple. On one hand, the potential for discovery is immense. Unlocking the secrets of black holes could revolutionize our understanding of gravity, space-time, and the very nature of reality. On the other hand, the risks, however remote, demand careful consideration. As we continue to explore these cosmic mysteries, we must weigh the benefits against the potential dangers, balancing our curiosity with a deep sense of responsibility. After all, the universe doesn't give us easy answers. It challenges us to think critically, act wisely, and dream boldly. And as we navigate this cosmic experiment together, one thing is certain: the journey is just as important as the destination. The future of black hole exploration is like a cosmic treasure hunt, with humanity armed with ever more powerful tools to uncover the universe's deepest secrets. As we peer into the vast expanse of space, new technologies and missions are set to revolutionize our understanding of these enigmatic objects, bringing us closer than ever to answering some of the most profound questions about the cosmos. From next-generation telescopes to advanced space probes, the horizon of discovery is brimming with promise, offering a glimpse into what lies beyond the event horizon. One of the most exciting developments is the next wave of space observatories, designed to see farther and with greater precision than ever before. Take the James Webb Space Telescope, for example. While not specifically built for black hole research, its ability to peer into the infrared spectrum allows us to study the environments around black holes in unprecedented detail. Then there's the upcoming Nancy Grace Roman Space Telescope, which will map the cosmos with incredible resolution, potentially revealing hidden black holes and their interactions with surrounding matter. These telescopes are like cosmic detectives, piecing together clues about how black holes form, grow, and influence their surroundings. But the real game changer could be the next generation of ground-based observatories, like the extremely large telescope currently under construction in Chile. With a mirror nearly the size of a football field, this telescope will capture images of black holes with stunning clarity, potentially revealing details about their accretion disks, jets, and even the elusive event horizon. It's like upgrading from a pair of binoculars to a high-powered microscope, allowing us to see the universe in a whole new light. Space probes are also set to play a crucial role in this cosmic quest. Missions like the European Space Agency's LISA project aim to detect gravitational waves from space, offering a new way to study black hole mergers and other cataclysmic events. By placing a trio of satellites millions of kilometers apart, LISA will act as a giant ear, listening for the faint ripples in space-time caused by black holes colliding. This could open up an entirely new window into the universe, revealing details about black holes that light-based telescopes simply can't capture. Scientists are buzzing with anticipation about what these tools might uncover. As astrophysicist Priyamvada Natarajan puts it, we're on the cusp of a new era in black hole research, where the questions we've been asking for decades might finally have answers. From understanding the role of black holes in galaxy formation to probing the nature of singularities, the possibilities are as vast as the universe itself. And then there's the tantalizing prospect of unexpected discoveries. As we push the boundaries of technology and knowledge, we might stumble upon phenomena that challenge everything we think we know. Could we find evidence of new types of black holes, or perhaps clues about the nature of dark matter and dark energy? The universe has a habit of surprising us, and the tools we're building today could be the keys to unlocking its greatest mysteries. The future of black hole exploration isn't just about answering questions, it's about asking new ones. Each discovery leads to deeper mysteries, sparking new avenues of research and inspiring the next generation of scientists. As we stand on the brink of this new frontier, one thing is certain: the journey is just beginning. With every new tool, every new mission, we're not just exploring black holes, we're uncovering the story of the universe itself. And who knows what treasures await us in the cosmic depths? The adventure has only just begun. In the quest to decode the mysteries of black holes, a new kind of detective has entered the scene. One that doesn't rely on telescopes or space probes, but on lines of code and algorithms. Artificial intelligence, or AI, is revolutionizing the way we study these cosmic enigmas, sifting through mountains of data with a precision and speed that would be impossible for humans alone. Think of AI as a cosmic sleuth, tirelessly combing through the noise of the universe to uncover hidden patterns, subtle signals, and unexpected phenomena. From identifying black hole mergers to simulating the chaotic environments around these gravitational giants, AI is becoming an indispensable tool in the astrophysicist's toolkit. The sheer volume of data generated by modern telescopes and observatories is staggering. Every second, instruments like the Event Horizon Telescope or the Large Synoptic Survey Telescope collect terabytes of information, images, spectra, and signals from across the cosmos. For human researchers, analyzing this data manually would be like searching for a needle in a galaxy-sized haystack. That's where AI steps in. Machine learning algorithms, trained to recognize specific patterns, can scan through this data in record time, identifying potential black hole candidates, gravitational wave events, or even anomalies that might hint at entirely new phenomena. It's like having a team of tireless detectives working around the clock, uncovering clues that might otherwise go unnoticed. One of the most exciting applications of AI in black hole research is its ability to detect gravitational waves, ripples in space-time caused by cataclysmic events like black hole mergers. When two black holes collide, they send out waves that travel across the universe, carrying information about their masses, spins, and orbits. Detecting these waves requires analyzing incredibly faint signals buried in a sea of noise. AI algorithms designed to pick out these subtle patterns have already proven their worth in projects like LIGO, where they've helped identify dozens of black hole mergers that might have been missed by traditional methods. As astrophysicist Karen Jani puts it, AI is like a magnifying glass for the cosmos, revealing details we never thought we'd see. But AI isn't just a passive observer, it's also helping us simulate the complex environments around black holes. By feeding vast amounts of data into machine learning models, researchers can create highly accurate simulations of accretion disks, jets, and other phenomena. These simulations allow us to test theories and make predictions about how black holes behave, offering insights that would be impossible to gain through observation alone. It's like having a virtual laboratory where we can experiment with the universe's most extreme conditions without ever leaving Earth. The potential for AI to uncover new insights about black holes is immense. Already, researchers are using AI to explore questions that have puzzled scientists for decades, such as the nature of singularities or the behavior of matter at the edge of a black hole. Some even speculate that AI could one day help us solve the black hole information paradox, a problem that has stumped physicists for years. As technology continues to evolve, the possibilities are endless. AI might reveal entirely new types of black holes, or uncover connections between black holes and other cosmic mysteries like dark matter. So, how will AI shape our understanding of black holes in the future? According to researchers, the impact could be transformative. AI is not just a tool, it's a paradigm shift, says astrophysicist Priyamvada Natarajan. It's allowing us to ask questions we couldn't even imagine before, and to explore the universe in ways that were once the realm of science fiction. As we continue to harness the power of AI, we're not just expanding our knowledge of black holes, we're redefining what it means to explore the cosmos. And with every discovery, we're reminded that the universe is full of surprises, waiting for us to uncover them. What other secrets might AI reveal as we peer deeper into the abyss? The answer might just change everything we think we know. Black holes have long transcended the boundaries of science, becoming a powerful source of inspiration in art, literature, and popular culture. These cosmic enigmas, with their mysterious allure and dramatic implications, have captured the human imagination like few other phenomena. They've become a cosmic muse, sparking creativity across countless mediums and inviting us to explore the unknown through both logic and emotion. From blockbuster films to haunting musical compositions, black holes have woven themselves into the fabric of our cultural consciousness, symbolizing everything from existential dread to the boundless potential of discovery. Take, for instance, the 2014 film Interstellar. Directed by Christopher Nolan and informed by the scientific expertise of physicist Kip Thorne, the movie brought black holes to life in stunning detail. The depiction of Gargantua, a supermassive black hole, wasn't just visually breathtaking, it was scientifically accurate, thanks to Thorne's calculations. The film's portrayal of time dilation near the black hole's event horizon became a pivotal plot point, blending hard science with deeply human storytelling. It's a perfect example of how black holes can serve as both a scientific concept and a narrative device, pushing us to confront questions about love, sacrifice, and our place in the universe. But it's not just movies. Black holes have also found their way into music, where their mysterious nature resonates with themes of infinity, isolation, and transformation. Artists like David Bowie and Muse have drawn inspiration from these cosmic phenomena, using them as metaphors for the unknown and the infinite. Bowie's iconic song, Black Star, for example, evokes the enigmatic and otherworldly qualities of black holes, while Muse's album Black Holes and Revelations explores themes of exploration and existential wonder. These works remind us that black holes aren't just scientific curiosities, they're symbols that tap into something deeply human, a reflection of our awe and curiosity about the cosmos. Visual artists, too, have been captivated by black holes. The swirling accretion disks and eerie silhouettes of these objects have inspired countless paintings, installations, and digital artworks. Some artists, like the team behind the Event Horizon Telescope's first image of a black hole, even collaborate directly with scientists to bring these cosmic giants to life. Others, like painter Leah Halloran, use black holes as a metaphor for the intersections of science and art, creating works that explore the beauty and mystery of the universe. As Halloran puts it, black holes are a perfect blend of science and imagination. They are places where the rules of reality bend, and so do the boundaries of creativity. This cultural fascination with black holes isn't just about their scientific intrigue, it's about what they represent. They're portals to the unknown, places where the familiar rules of physics break down and the imagination can run wild. For scientists, they're a frontier of discovery, offering clues about the nature of space-time and the origins of the universe. For artists, they're a canvas for exploring themes of infinity, transformation, and the human condition. And for all of us, they're a reminder of how small we are in the grand scheme of things, yet how vast our capacity for wonder remains. The interplay between science and art around black holes is more than just a meeting of disciplines, it's a dialogue about the human experience. Scientists like Carl Sagan and Neil deGrasse Tyson have often spoken about the poetic beauty of the cosmos, while artists like Olafur Eliasson have used their work to evoke the emotional impact of astronomical phenomena. Together, they remind us that black holes are not just objects of study, they're symbols of our endless quest to understand the universe and ourselves. As we continue to explore the mysteries of black holes, their cultural impact will only grow. They'll remain a source of inspiration for storytellers, musicians, and artists, inviting us to imagine what lies beyond the event horizon and what it means to confront the unknown. And as we peer into the depths of these cosmic wonders, one thing is certain: black holes will continue to captivate us, not just as scientific marvels, but as reflections of our deepest hopes, fears, and dreams. What new stories, songs, or visions might they inspire in the years to come? The answer lies at the intersection of science, art, and the boundless human imagination. Black holes are more than just cosmic phenomena. They are mirrors reflecting some of the deepest questions humanity has ever asked. Staring into their infinite depths, we're confronted with mysteries that go beyond science and touch the very essence of what it means to exist. What is reality? What is time? And where do we, as tiny beings in an unfathomably vast universe, fit into it all? These are questions that have puzzled philosophers for centuries, and black holes, with their mind-bending properties, bring them into sharp focus. They challenge us to rethink everything we thought we knew, not just about the cosmos, but about ourselves. Consider the nature of reality. To us, reality seems solid and predictable, a world governed by rules we can understand and measure. But black holes shatter that illusion. Near the event horizon, time slows to a crawl. Inside the singularity, the very fabric of space and time breaks down. These phenomena force us to ask, is reality as we experience it just a small slice of a much larger, more complex truth? Philosophers like Immanuel Kant argued that our perception of reality is shaped by our senses and our minds, limiting what we can truly know. Black holes seem to echo this idea, revealing a universe that operates on scales and in ways far beyond our everyday understanding. Time, too, takes on a different meaning when viewed through the lens of a black hole. In our daily lives, time flows in one direction forward, but near a black hole, time becomes malleable, stretching and warping under the influence of immense gravity. This raises profound questions. Is time truly linear, or is it just an illusion created by our limited perspective? Scientists like Carlo Rovelli have explored the idea that time might not even exist as a fundamental property of the universe, but rather as an emergent phenomenon, a byproduct of more basic interactions. Black holes, with their ability to twist time into knots, challenge us to rethink the very nature of this dimension we take for granted. And then there's the question of existence itself. Black holes are places where matter is compressed into an infinitely small point, where the rules of physics as we know them no longer apply. What happens to the information about the matter that falls in? Is it lost forever, or does it somehow persist, encoded in ways we can't yet comprehend? These questions touch on the very essence of being and non-being, themes that philosophers from Plato to Heidegger have grappled with. Black holes remind us that existence might not be as straightforward as we think. that there are layers of reality we're only beginning to glimpse. Black holes also challenge our sense of place in the universe. They are cosmic reminders of how small and fleeting we are in the grand scheme of things. Yet at the same time, they inspire awe and curiosity, driving us to explore and understand the cosmos. This duality of insignificance and potential resonates deeply with the human experience. Philosophers like Albert Camus have explored the tension between the absurdity of life in an indifferent universe and the human drive to find meaning. Black holes, in a way, embody this tension. They are both a symbol of the universe's indifference and a source of endless fascination, urging us to keep asking questions and seeking answers. So, what do black holes teach us about the meaning of life? Perhaps they remind us that meaning isn't something inherent in the universe, but something we create through our curiosity, our exploration, and our connections to one another. They invite us to look beyond the surface, to question our assumptions, and to embrace the unknown. In that sense, black holes aren't just cosmic curiosities. They are teachers, challenging us to think bigger, to dream deeper, and to find beauty in the mysteries that surround us. What other lessons might these cosmic mirrors hold, waiting for us to discover? The journey to find out is as profound as the questions themselves. When we think about the search for extraterrestrial life, our minds often drift to distant planets, icy moons, or the atmospheres of exoplanets. But what if the key to finding life beyond Earth lies not in these familiar places, but in the most extreme environments in the universe, black holes? It might seem counterintuitive, but these cosmic giants could play a surprising role in the quest for life. Imagine a black hole not as a destructive force, but as a cosmic beacon, a signal that might guide us, or even other civilizations, toward the possibility of life. This idea, once relegated to the realm of science fiction, is now being explored by astrobiologists and astrophysicists alike, offering a new perspective on where life might exist in the universe. One intriguing possibility is that black holes could create habitable zones in their vicinity. While the event horizon itself is a place of no return, the regions surrounding a black hole are anything but barren. Supermassive black holes, for instance, often have swirling accretion disks of gas and dust that can heat up to incredible temperatures, emitting radiation and energy. In some cases, this radiation could provide enough warmth to sustain liquid water on nearby planets or moons, a key ingredient for life as we know it. It's like a black hole acting as a cosmic furnace, keeping distant worlds warm in the cold void of space. These habitable zones around black holes might not be as hospitable as Earth, but they could offer just enough stability for life to take hold. But black holes might also serve as markers for advanced civilizations. If a technologically advanced species were to harness the energy of a black hole, perhaps by extracting power from its accretion disk or even its rotation, they might leave behind detectable signatures. For example, a civilization using a black hole as a power source could emit specific patterns of radiation or gravitational waves, creating a kind of cosmic fingerprint. These signals, while faint, could be picked up by our telescopes or detectors, offering a tantalizing clue that we're not alone in the universe. In this way, black holes could act as lighthouses, guiding us toward regions of space where intelligent life might thrive. Astrobiologists are particularly fascinated by the idea that black holes could influence the evolution of life in unexpected ways. The intense radiation and gravitational forces near a black hole might drive the development of unique life forms, adapted to survive in conditions that would be lethal elsewhere. Some scientists speculate that microbial life, for instance, could exist in the outer regions of an accretion disk, feeding on the energy-rich environment. Others suggest that black holes could act as cosmic incubators, seeding the universe with the building blocks of life through their jets and outflows. It's a reminder that life, if it exists, might be far more adaptable and resilient than we've ever imagined. The implications for the search for extraterrestrial life are profound. If black holes can create habitable zones or serve as markers for advanced civilizations, they could drastically expand the scope of our search. Instead of focusing solely on Earth-like planets, we might also look toward the regions around black holes where the rules of habitability are rewritten. This shift in perspective could open up entirely new avenues for exploration, from studying the radiation signatures of distant black holes to searching for anomalies in their gravitational waves. As astrobiologist Avi Loeb has noted, the universe is full of surprises, and black holes might be hiding some of its greatest secrets. So, what clues might black holes hold about the existence of alien civilizations? Could they be the key to unlocking one of humanity's oldest questions? Are we alone in the universe? The answers might be hidden in the swirling disks, powerful jets, and mysterious emissions of these cosmic giants. As we continue to explore the mysteries of black holes, we're not just uncovering the secrets of gravity and space-time, we're searching for signs of life itself. And who knows, the next great discovery might just reveal that black holes are more than cosmic wonders, they're gateways to the unknown, pointing us toward the possibility of life beyond our wildest dreams. Imagine a cosmic whirlpool spinning with such ferocity that it drags the very fabric of space-time along with it. This isn't the stuff of science fiction, it's the reality of black hole spin, a phenomenon that transforms these gravitational giants into dynamic, swirling engines of the cosmos. Unlike their static portrayal in popular culture, black holes aren't just static voids. Many of them are spinning at incredible speeds, warping the universe around them in ways that defy our everyday experience of space and time. This spin isn't just a curiosity, it's a fundamental property that shapes how black holes interact with their surroundings, from the swirling accretion disks of superheated gas to the powerful jets of particles that shoot out into space. To understand how spin works, think of a black hole as a cosmic top, rotating faster and faster as it pulls in matter and energy. As it spins, it drags space-time around with it, a phenomenon known as frame dragging. Picture a spoon stirring honey. The honey closest to the spoon moves the fastest, while the rest is pulled along more slowly. In the same way, a spinning black hole twists the space-time around it, creating a vortex that affects everything nearby. This spinning motion doesn't just influence the black hole itself, it shapes the behavior of matter and light in its vicinity, creating environments that are both chaotic and strangely ordered. The effects of black hole spin are especially dramatic near the event horizon, where the pull of gravity is at its strongest. Here, the swirling space-time can cause particles and radiation to spiral inward at incredible speeds, heating up to billions of degrees and emitting intense bursts of energy. This process powers the accretion disks that surround many black holes, turning them into some of the brightest objects in the universe. But spin doesn't just fuel these cosmic engines, it also influences the direction and intensity of the jets that shoot out from the black hole's poles. These jets, which can stretch for thousands of light years, are thought to be driven by the black hole's rotation, acting like cosmic particle accelerators that blast matter and energy into the void. Measuring the spin of a black hole is no easy task, but scientists have developed ingenious methods to do just that. One approach involves studying the X-rays emitted by the accretion disk. As matter spirals inward, it heats up and emits radiation, with the innermost edge of the disk revealing clues about the black hole's spin. By analyzing the spectrum of this radiation, scientists can determine how fast the black hole is rotating. Another method relies on observing the gravitational waves produced when two black holes collide, as the spin of the merging objects leaves a distinct signature in the ripples of space-time. These techniques have allowed researchers to measure the spins of black holes across the universe, revealing a surprising diversity in their rotation rates. The significance of black hole spin extends far beyond the black holes themselves. It plays a crucial role in the evolution of galaxies, influencing how black holes grow and interact with their surroundings. For instance, the spin of a supermassive black hole can determine the shape and structure of its host galaxy, affecting the formation of stars and the movement of gas. Physicists like Kip Thorne have described spin as a cosmic fingerprint, a unique characteristic that shapes the behavior of black holes and the universe around them. As Thorne puts it, spin is the hidden hand that guides the dance of matter and energy near black holes, shaping the cosmos in ways we're only beginning to understand. So, how does black hole spin shape the universe around it? The answer lies in the intricate interplay between gravity, rotation, and spacetime, a cosmic dance that influences everything from the birth of stars to the structure of galaxies. As we continue to explore the mysteries of black hole spin, we're uncovering new insights into the forces that drive the universe, revealing a cosmos that's far more dynamic and interconnected than we ever imagined. What other secrets might these spinning giants hold, waiting to be discovered? The journey to find out is just beginning. Black holes are often seen as cosmic destroyers, devouring everything in their path. But what if they're also cosmic architects, quietly shaping the universe on the grandest scales? From the birth of galaxies to the sprawling cosmic web that connects them, black holes play a pivotal role in the evolution of the cosmos. Think of them as cosmic engineers, not just tearing things apart, but also building the structures that define the universe we see today. Their influence stretches far beyond their event horizons, weaving a complex tapestry of matter, energy, and gravity that shapes the destiny of everything around them. At the heart of this cosmic engineering is a process known as feedback. Black holes, especially supermassive ones, don't just sit quietly at the centers of galaxies. They actively interact with their surroundings. When a black hole feeds on gas and dust, it doesn't do so silently. Instead, it releases tremendous amounts of energy in the form of radiation and powerful jets of particles. These outbursts can heat up the surrounding gas, preventing it from cooling and collapsing into stars. It's like a cosmic thermostat, regulating the temperature and density of the galaxy's building blocks. This feedback mechanism ensures that galaxies don't grow too quickly, maintaining a delicate balance between creation and destruction. But black holes don't just suppress star formation, they can also trigger it. In some cases, the shock waves from their jets compress gas clouds, sparking the birth of new stars. It's a bit like lighting a match in a field of dry grass, creating pockets of fire where none existed before. This dual role, suppressing and stimulating star formation, makes black holes pivotal players in the life cycle of galaxies. They're not just passive observers, they're active participants, shaping the evolution of galaxies in profound and often unexpected ways. The influence of black holes extends even further into the very fabric of the cosmic web. This vast network of filaments and voids, made up of dark matter and gas, connects galaxies across the universe. Black holes, with their immense gravitational pull and energetic jets, play a key role in shaping this web. Their jets can push gas out into the intergalactic medium, redistributing matter and influencing the formation of galaxy clusters. It's as if black holes are cosmic sculptors, carving out the large-scale structure of the universe and guiding the flow of matter on scales we can barely comprehend. Cosmologists have long been fascinated by this interplay between black holes and the cosmic web. As astrophysicist Primordial Natarajan explains, black holes are not just isolated objects, they're deeply embedded in the cosmic network, influencing and being influenced by the universe around them. This interconnectedness suggests that black holes are more than just local phenomena, they're integral to the evolution of the cosmos as a whole. From the smallest galaxies to the largest superclusters, their fingerprints are everywhere, shaping the universe in ways we're only beginning to understand. So, what does this mean for the future of the universe? As black holes continue to grow and interact with their surroundings, they'll play an even greater role in shaping the cosmos. Over billions of years, their feedback loops and gravitational influence will determine how galaxies evolve, how matter is distributed, and even how the cosmic web itself changes. They're not just relics of the past, they're active agents in the ongoing story of the universe. As we peer deeper into the cosmos, we're uncovering the profound ways in which black holes shape the universe's destiny. They're not just cosmic engines or destructive forces, they're architects, sculptors, and regulators, quietly guiding the evolution of everything around them. And as we continue to explore their mysteries, one question lingers: what other cosmic blueprints might these giants hold, waiting to be discovered? The answer lies in the stars and the black holes that shape them. At first glance, a black hole seems like the ultimate chaos, a place where matter is crushed into oblivion, and the laws of physics as we know them break down. But beneath this apparent disorder lies a surprising order, a hidden structure that connects black holes to one of the most fundamental branches of science, thermodynamics. This connection is rooted in a concept called black hole entropy, a measure of the disorder or randomness within a black hole. It's a bit like finding a cosmic thermometer in the heart of a storm, revealing that even in the most chaotic environments, there's an underlying order waiting to be understood. To grasp the idea of black hole entropy, let's start with something familiar: a cup of coffee. When you pour cream into your coffee, the two liquids mix, creating a swirling, chaotic pattern. Over time, the mixture settles into a uniform state, a process driven by entropy, which measures the increase in disorder. Now, imagine scaling this up to a cosmic level. A black hole, with its immense gravitational pull, swallows matter and energy, increasing the disorder of the universe. But unlike the coffee, this disorder isn't visible. It's encoded in the black hole's entropy, a property that tells us how much information is hidden within its event horizon. The idea of black hole entropy was first proposed by physicist Jacob Bekenstein in the 1970s, and it was a revelation that shook the foundations of physics. Bekenstein argued that black holes must have entropy because they absorb matter and energy, effectively increasing the disorder of the universe. This discovery connected black holes to the laws of thermodynamics, which govern heat, energy, and the behavior of systems. It's as if black holes, once thought to be cosmic outliers, are actually deeply tied to the same principles that govern everything from steam engines to stars. As physicist Leonard Susskind put it, black holes are the ultimate thermodynamic objects. They're where gravity and entropy meet. But what does black hole entropy mean for our understanding of the universe? For one, it suggests that black holes aren't just gravitational wells, they're complex thermodynamic systems with their own temperature and energy. This connection has profound implications, particularly when it comes to the nature of information. According to quantum mechanics, information can never be truly destroyed, yet black holes seem to defy this rule by swallowing matter and energy without a trace. Black hole entropy offers a potential solution. The information isn't lost, it's encoded on the black hole's event horizon, like a cosmic hard drive preserving the details of everything that falls in. The implications of this idea stretch far beyond black holes themselves. It hints at a deeper unity between the laws of physics, suggesting that gravity, quantum mechanics, and thermodynamics might all be part of a larger, more interconnected framework. This connection has inspired some of the most groundbreaking work in modern physics, from the holographic principle, which suggests that the universe might be a kind of hologram, to the quest for a unified theory that ties together all the fundamental forces of nature. As physicist Juan Maldacena notes, black hole entropy is a clue, a piece of the puzzle that might help us understand the universe on its deepest levels. So, what does black hole entropy tell us about the nature of the universe? It's a question that challenges us to rethink everything we thought we knew about order and disorder, about the flow of time, and about the very fabric of reality. Black holes, once seen as cosmic destroyers, might actually hold the key to understanding the universe's most profound mysteries. As we continue to explore this connection, one thing is clear: the cosmos is far more intricate and interconnected than we ever imagined. And in the hidden order of black hole entropy, we might just find the answers we've been searching for all along. Imagine stepping into a cosmic machine, one that bends the rules of time itself. Black holes, with their immense gravitational pull, have long been theorized as potential gateways to time travel, a concept that sounds like science fiction but is rooted in some of the most intriguing ideas in physics. At the heart of this speculation lies the concept of closed time-like curves, paths through space-time that loop back on themselves, allowing for the possibility of traveling back in time. Picture a river flowing in a circle where the water eventually returns to its starting point. In the same way, a closed time-like curve could theoretically allow an object or even a person to revisit the past. But how could something as extreme as a black hole make this possible? The key lies in how black holes warp space-time. Near the event horizon, gravity becomes so intense that time slows down dramatically, a phenomenon known as gravitational time dilation. For someone orbiting close to a black hole, time would pass much more slowly compared to someone far away. This effect, predicted by Einstein's theory of general relativity, has been confirmed through experiments and observations. But what if we could harness this extreme distortion of time? Some physicists speculate that under the right conditions, the intense gravitational field of a black hole could create a stable closed time-like curve, effectively turning the black hole into a cosmic time machine. To visualize this, think of space-time as a rubber sheet. A massive object like a black hole creates a deep well in this sheet, bending and twisting it. If the well is deep enough and shaped in just the right way, it could form a loop, a closed time-like curve that allows for time travel. This idea has captured the imagination of scientists and science fiction writers alike, offering a tantalizing glimpse into what might be possible if we could navigate the extreme environments near black holes. But as physicist Kip Thorne has pointed out, the math allows for it, but the practical challenges are immense. Creating or finding such a curve would require conditions far beyond anything we've ever encountered, making time travel a theoretical possibility rather than a practical one. The implications of time travel through black holes stretch beyond science into philosophy. If time travel were possible, what would it mean for our understanding of cause and effect? Could we change the past, or would our actions simply become part of the timeline we're trying to alter? These questions challenge our notions of free will, destiny, and the nature of reality itself. As physicist Stephen Hawking once quipped, "If time travel is possible, where are all the tourists from the future?" His playful skepticism highlights the paradoxes that arise when we consider the possibility of bending time. Despite the challenges, the idea of black holes as time machines continues to inspire research and speculation. Some theories suggest that rotating black holes or Kerr black holes might offer the necessary conditions for closed time-like curves. Others explore the potential of wormholes, hypothetical tunnels through space-time that could connect distant points or even different times. While these ideas remain speculative, they push the boundaries of our understanding and invite us to imagine what might be possible in the far reaches of the universe. So, could black holes unlock the secrets of time? The answer lies in the delicate interplay between gravity, space-time, and the laws of physics. While the practicalities of time travel remain out of reach, the theoretical possibilities remind us that the universe is full of surprises waiting for us to uncover them. As we continue to explore the mysteries of black holes, we might just find that the key to understanding time itself is hidden in their swirling depths. What other secrets might these cosmic giants hold waiting to be discovered? The journey to find out is just beginning. When we think about the defining properties of a black hole, mass and spin often take center stage. But there's a third, often overlooked characteristic that plays a crucial role in shaping these cosmic giants: electric charge. Imagine a black hole not just as a gravitational powerhouse, but as a cosmic battery, storing energy that can influence its surroundings in surprising ways. This charge, though less discussed, is a key piece of the puzzle that defines how black holes interact with the universe around them. But what exactly is black hole charge, and how does it fit into the grand tapestry of astrophysics? To understand black hole charge, picture a massive object like a star or a gas cloud collapsing into a black hole. If that object carried an electric charge, perhaps due to an imbalance of protons and electrons, that charge would be preserved as the black hole forms. The result is a black hole with an electric field, a bit like a star that's been compressed into a gravitational titan but still retains a faint spark of its former self. This charge doesn't just sit idly by. It interacts with the black hole's environment, shaping the behavior of matter and energy in its vicinity. It's as if the black hole has a hidden layer of complexity, one that adds a new dimension to its already mysterious nature. The effects of black hole charge are subtle but profound. For instance, a charged black hole can repel or attract charged particles, creating a dynamic interplay between the black hole and its surroundings. This interaction can influence the formation of accretion disks, the swirling rings of superheated gas that feed black holes, and even the powerful jets that shoot out from their poles. In some cases, the charge might act like a cosmic conductor, guiding the flow of matter and energy in ways that a neutral black hole couldn't. It's a reminder that black holes, despite their reputation as cosmic vacuums, are far more nuanced than we often give them credit for. Detecting black hole charge, however, is no simple task. Unlike mass and spin, which leave clear imprints on the behavior of matter and light, charge is much harder to observe directly. One reason is that most black holes are thought to be electrically neutral, as any excess charge would quickly attract opposite charges from their surroundings, neutralizing the effect. Still, some theoretical models suggest that charged black holes could exist under specific conditions, such as in environments with strong magnetic fields or in the early universe. Scientists have proposed looking for subtle signatures in the way charged black holes interact with their surroundings, from the structure of their accretion disks to the behavior of particles near the event horizon. But for now, charged black holes remain elusive, their existence more a tantalizing possibility than a confirmed reality. The significance of black hole charge extends beyond the cosmic mechanics of these objects. It's a reminder that even the most extreme phenomena in the universe are governed by the same fundamental forces we experience here on Earth. As physicist Roger Penrose once noted, black holes are not just cosmic curiosities, they are laboratories for testing the laws of physics in their most extreme form. Charge, as one of the three defining properties of a black hole, offers a unique window into these laws, helping us understand how gravity, electromagnetism, and quantum mechanics intertwine in the heart of a black hole. So, how does black hole charge influence the universe? The answer might lie in the subtle ways it shapes the behavior of matter and energy, from the swirling disks that feed black holes to the jets that light up the cosmos. It's a question that invites us to look deeper, to explore the hidden layers of complexity that define these enigmatic objects. And as we continue to unravel the mysteries of black hole charge, we're reminded that the universe is full of surprises waiting for us to uncover them. What other secrets might these cosmic batteries hold, and how might they reshape our understanding of the cosmos? The journey to find out is just beginning. Black holes aren't just cosmic oddities, they're also the ultimate testing grounds for one of the most profound questions in physics: how to unite quantum mechanics and general relativity. These two pillars of modern science work beautifully in their own domains: quantum mechanics explaining the behavior of the very small, and general relativity governing the very large. But when it comes to black holes, where the immense gravity of a singularity meets the bizarre rules of the quantum world, the two theories clash in spectacular fashion. It's as if black holes are a cosmic laboratory, offering a rare glimpse into the intersection of these two realms and pushing us to rethink the very fabric of reality. To understand why black holes are so crucial to this quest, imagine trying to solve a puzzle where half the pieces are made of wood and the other half of glass. Quantum mechanics and general relativity are like those mismatched pieces, fundamentally different in their structure and behavior, yet both essential to completing the picture. Black holes, with their extreme gravitational fields and quantum scale phenomena, force us to confront this incompatibility head-on. Near the event horizon, particles and antiparticles pop in and out of existence, warping space-time in ways that defy our current understanding. It's a place where the quantum and the cosmic collide, creating a perfect storm of scientific intrigue. Studying quantum effects near black holes is no easy task. The scales involved are mind-bogglingly small. Think of particles smaller than atoms interacting with gravitational forces so immense they can bend light itself. This makes direct observation nearly impossible, leaving physicists to rely on theoretical models and indirect evidence. Yet, despite the challenges, black holes offer a unique opportunity to test ideas about quantum gravity, the long-sought theory that would unify these two domains. For instance, the holographic principle, which suggests that all the information about a black hole is encoded on its surface, is one such idea that has gained traction. It's like a cosmic Rosetta Stone, offering clues about how to translate between the languages of quantum mechanics and general relativity. Physicists like Leonard Susskind and Juan Maldacena have likened black holes to cosmic experiments, where the extreme conditions allow us to probe the limits of our theories. Susskind, in particular, has championed the idea that black holes are key to understanding the nature of spacetime itself. Black holes are where gravity and quantum mechanics meet, he says. They're the ultimate testing ground for new ideas, pushing us to think beyond the boundaries of what we know. This perspective has inspired a wave of research, from studying the quantum properties of Hawking radiation to exploring the possibility that spacetime itself might emerge from more fundamental quantum interactions. The potential breakthroughs in understanding quantum gravity are immense. A successful theory could revolutionize our understanding of the universe, answering questions about the nature of singularities, the origins of spacetime, and even the fate of information swallowed by black holes. It's a quest that has captivated physicists for decades, with each new discovery bringing us closer to a unified framework. And while the path forward is far from clear, black holes remain our best hope for finding the answers. So, what secrets might black holes hold about the universe's deepest mysteries? Could they reveal the true nature of spacetime, or even the origins of the cosmos itself? As we continue to explore these cosmic laboratories, one thing is certain. Black holes are more than just gravitational giants, they're the keys to unlocking the next great chapter in our understanding of the universe. And with every new insight, we're reminded that the cosmos is full of surprises, waiting for us to uncover them. What other revelations might these enigmatic objects hold? The journey to find out is just beginning. Deep in the void of space, where black holes warp the fabric of reality, there's a phenomenon that sounds almost like a cosmic whisper: black hole echoes. These subtle reverberations, born from the collision of gravitational waves with the event horizon, offer a rare opportunity to listen to the universe in a way we've never done before. Picture a stone dropped into a still pond. The ripples spread outward, bounce off the edges, and return as faint echoes. In the same way, when gravitational waves, ripples in space-time, interact with the edge of a black hole, they can reflect back, carrying with them secrets about the black hole's structure and the nature of space-time itself. These echoes aren't just faint signals, they're cosmic breadcrumbs guiding us toward a deeper understanding of the universe's most enigmatic objects. Detecting these echoes, however, is no small feat. Gravitational waves, first detected in 2015 by the LIGO Observatory, are already incredibly faint, and their echoes are even more elusive. To catch these whispers, scientists rely on sophisticated algorithms and advanced detectors, sifting through the noise of the cosmos to isolate the subtle patterns left behind. It's like trying to hear a single voice in a crowded stadium where every sound is amplified and distorted. Yet, despite the challenges, researchers are making strides, using techniques like machine learning and pattern recognition to identify these faint signals. Each echo, no matter how faint, holds the potential to unlock new insights into the mysteries of black holes and the fabric of space-time. What makes black hole echoes so fascinating is what they might reveal. Unlike the direct gravitational waves produced by black hole collisions, echoes carry information about the event horizon itself, the boundary beyond which nothing can escape. Some theories suggest that these echoes could provide evidence of exotic structures near the black hole, such as quantum fuzzballs or other phenomena that challenge our current understanding of physics. Others propose that echoes might help us test Einstein's theory of general relativity in the most extreme conditions, offering clues about how gravity behaves at the edge of a black hole. As physicist Nayesh Afshordi explains, black hole echoes could be the key to uncovering new physics, revealing a side of the universe we've never seen before. The search for these echoes isn't just about refining our understanding of black holes, it's about probing the very nature of space-time. If echoes exist, they could offer a glimpse into the quantum structure of space-time, a realm where the smooth, continuous fabric predicted by general relativity might break down into something more granular. This idea, often referred to as quantum foam, suggests that space-time itself might have a texture at the smallest scales, like the surface of a bubbling pot of water. Black hole echoes could be the first hint of this hidden world, a cosmic whisper that hints at the universe's deepest secrets. So, what can black hole echoes tell us about the nature of space-time? The answer might lie in the subtle patterns they leave behind, patterns that could rewrite our understanding of gravity, quantum mechanics, and the fundamental laws of the cosmos. As we continue to listen for these faint whispers, one thing is certain: the universe is speaking to us, and black hole echoes might just be the language we need to decode its message. What other secrets might these cosmic whispers hold, waiting for us to uncover? The journey to find out is just beginning. Black holes are often seen as the ultimate cosmic consumers, devouring everything in their path. But what if they're also the universe's greatest recyclers? Far from being mere destroyers, black holes play a vital role in the cosmic cycle of matter and energy, acting as both consumers and creators in the grand tapestry of the universe. Imagine a cosmic furnace where matter is pulled in, transformed, and then expelled back into the cosmos in a continuous cycle of creation and renewal. This process, known as accretion, is the engine that drives black holes' role in cosmic recycling. At the heart of this cycle is the accretion disk, a swirling vortex of gas, dust, and debris that spirals inward toward the black hole's event horizon. As matter falls into this disk, it heats up to incredible temperatures, emitting vast amounts of energy in the form of radiation and light. But not all of this matter is destined to be swallowed. Some of it is flung outward in powerful jets, propelled by the black hole's intense magnetic fields and rotational energy. These jets, which can stretch for thousands of light years, carry matter and energy far beyond the black hole's reach, seeding the surrounding space with the raw materials for new stars and galaxies. It's as if the black hole is a cosmic recycler, taking in old matter and spitting out fresh ingredients for the universe's next act. This process has profound implications for the life cycle of galaxies. When a black hole ejects matter into its surroundings, it can trigger the formation of new stars, effectively turning a region of space into a stellar nursery. But black holes can also halt star formation by heating up gas clouds, preventing them from collapsing and igniting. This dual role, both nurturing and regulating star formation, makes black holes key players in the cosmic balance. Astrophysicist Priyamvada Natarajan describes this interplay as a cosmic dance, where black holes and galaxies grow together, shaping each other's destinies over billions of years. The impact of black holes on cosmic recycling goes even further. By redistributing matter and energy across vast distances, they help maintain the large-scale structure of the universe. The jets and outflows from supermassive black holes, for example, can travel across entire galaxy clusters, influencing the formation of new structures and the evolution of existing ones. This process ensures that matter is constantly being cycled through the universe, from the smallest particles to the largest galaxies. As cosmologist Martin Rees once noted, black holes are not just endpoints, they are conduits, channels through which the universe renews itself. So, what does this mean for the universe as a whole? Black holes are more than just gravitational giants. They are cosmic recyclers, playing a crucial role in the ongoing cycle of creation and destruction. From the birth of stars to the evolution of galaxies, their influence is woven into the very fabric of the cosmos. And as we continue to explore their mysteries, one thing becomes clear. Black holes are not just consumers of the universe, they are its sustainers, quietly maintaining the balance that allows the cosmos to thrive. What other secrets might these cosmic recyclers hold, and how might they shape the future of the universe? The answers are waiting to be discovered, hidden in the swirling depths of these enigmatic giants. Imagine taking a cosmic selfie, not of a familiar face, but of a shadow cast by one of the most mysterious objects in the universe, a black hole. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow in the galaxy M87, a groundbreaking achievement that felt like humanity's first glimpse into the abyss. But M87 is just one galaxy among billions. What would it take to capture images of black hole shadows in other galaxies? And what could these snapshots reveal about the diversity and behavior of these cosmic giants? The answer lies in a quest that pushes the limits of technology, patience, and our understanding of the universe. The challenge of imaging black hole shadows in other galaxies is immense, akin to trying to photograph a tiny speck of dust on the surface of a distant star. Black holes, even supermassive ones, are incredibly small relative to the vast distances between galaxies. To capture their shadows, scientists need an array of telescopes with unprecedented resolution, spread across the globe, working in perfect synchrony. The Event Horizon Telescope, a global network of observatories, achieved this for the first time by combining data from multiple locations to create a virtual telescope the size of Earth itself. But extending this technique to other galaxies introduces new hurdles, from the faintness of distant black holes to the interference of cosmic dust and gas. Despite these challenges, the potential rewards are enormous. Each black hole shadow is like a unique fingerprint, revealing details about the black hole's mass, spin, and the structure of its accretion disk. By studying these shadows in different galaxies, astronomers can explore the astonishing diversity of black holes, from the relatively quiet giants at the centers of spiral galaxies to the hyperactive behemoths powering distant quasars. These images could also test the universality of Einstein's theory of general relativity, offering clues about how gravity behaves in the most extreme environments across the cosmos. Astronomers are already looking to the future with plans to expand the Event Horizon Telescope's capabilities and improve its resolution. New telescopes, like the proposed next-generation Very Large Array, promise to enhance our ability to peer into the hearts of distant galaxies. As astrophysicist Shepard Doleman, who led the first black hole imaging project, puts it, every new image is a window into the unknown, a chance to see the universe in a way we've never seen before. These efforts could one day reveal a gallery of black hole shadows, each telling its own story about the evolution and structure of the cosmos. So, what can black hole shadows in other galaxies teach us about the universe? They might hold clues about how black holes form and grow, how they interact with their host galaxies, and even how the universe itself has evolved over billions of years. Each shadow is a piece of a cosmic puzzle, helping us understand the intricate dance of matter, energy, and gravity that shapes the universe. As we continue to push the boundaries of observation, one thing is certain: the universe is full of surprises waiting for us to uncover them. What other secrets might these cosmic shadows hold, and how might they reshape our understanding of the cosmos? The journey to find out has only just begun. Black holes are more than just cosmic oddities. They are windows into the unknown, offering us a chance to peer beyond the edges of our current understanding of physics. Imagine them as cosmic laboratories, where the extreme conditions at their edges and within their depths allow us to test theories that go far beyond the standard model, the framework that has guided physics for decades. Here, in the intense gravitational fields and warped space-time near black holes, the rules of the universe as we know them begin to bend, revealing glimpses of phenomena that might otherwise remain hidden. One of the most tantalizing possibilities is that black holes could help us uncover evidence of extra dimensions. According to some theories, like string theory, our universe might have more than the 3 spatial dimensions we experience. These extra dimensions could be curled up and hidden from view, but near a black hole, their effects might become detectable. For instance, the way a black hole's gravity behaves or the way it interacts with matter could show subtle deviations from what our current models predict, hinting at the presence of these unseen dimensions. It's like opening a door to a hidden room in the cosmic mansion, revealing spaces we never knew existed. Black holes might also hold the key to discovering new particles. The intense energies near the event horizon could create conditions where exotic particles, predicted by theories beyond the standard model, are briefly brought into existence. These particles, which might include dark matter candidates or even entirely new forms of matter, could leave behind faint signatures in the radiation or gravitational waves emitted by black holes. Detecting these signals would be like finding a treasure map hidden in the cosmic noise, guiding us toward a deeper understanding of the building blocks of the universe. Physicists are already excited about the possibilities. As theoretical physicist Maria Spyropoulou explains, black holes are the ultimate probes for new physics. They push our theories to their limits and force us to think beyond the boundaries of what we know. This sentiment is echoed by researchers working on projects like the Event Horizon Telescope and gravitational wave detectors, who see black holes as more than just objects of study. They are tools for discovery, offering insights that could reshape our understanding of reality itself. The implications of these discoveries are profound. If black holes reveal evidence of extra dimensions or new particles, it could revolutionize not just physics but our entire worldview. It would mean that the universe is far more complex and interconnected than we ever imagined, with layers of reality waiting to be uncovered. It's a bit like realizing that the world we thought was flat is actually part of a vast, multidimensional landscape full of hidden pathways and uncharted territories. So, what might black holes teach us next? Could they be the key to unlocking the secrets of dark matter, or even the origins of the universe itself? As we continue to explore these cosmic laboratories, one thing is certain: black holes are not just endpoints of curiosity, they are gateways to new frontiers of knowledge. And with every discovery, we take another step toward understanding the universe's deepest mysteries. The journey is just beginning, and the possibilities are as vast as the cosmos itself. From the mind-bending distortions of the event horizon to the fiery jets that light up entire galaxies, black holes have taken us on a journey through some of the most extreme and mysterious phenomena in the universe. We've explored how these cosmic giants warp spacetime, how they might serve as portals to other dimensions, and how they recycle matter and energy on a scale that defies imagination. We've peered into the shadows of black holes, listened to the echoes of their collisions, and even questioned whether they could unlock the secrets of time itself. Each discovery challenges our understanding of reality, pushing the boundaries of what we thought was possible. These insights remind us that the universe is far stranger and more interconnected than we often realize. Black holes are not just cosmic curiosities, they are windows into the unknown, offering clues about the fundamental forces that shape existence. They force us to confront questions about the nature of spacetime, the fate of information, and even the origins of the cosmos. As physicist Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Black holes embody that sentiment, inviting us to keep exploring, keep questioning, and keep marveling at the wonders of the universe. But the journey doesn't end here. Every answer we find leads to new questions. Every discovery opens the door to deeper mysteries. The exploration of black holes is far from over, and with each new telescope, each new experiment, we inch closer to uncovering the secrets they hold. This is why continued research is so vital. It's not just about satisfying curiosity, but about expanding our understanding of the cosmos and our place within it. So, what do you think lies beyond the edge of a black hole? What other secrets might these cosmic enigmas hold? Let us know your thoughts and questions in the comments below. We'd love to hear your ideas and theories. And if you enjoyed this deep dive into the mysteries of black holes, don't forget to subscribe for more explorations into the wonders of space. The universe is vast and its mysteries are endless. Together, let's keep looking up, keep asking questions, and keep uncovering the incredible stories written in the stars. The next great discovery could be just around the corner, waiting for us to find it.